Hi everyone, so this is a continuation video on solving wave equation. In today's class we are gonna continue to look at the simple examples of wave equations such as the vibration string. Okay, for the vibration string we are gonna look at infinite region or infinite interval. Okay, now you can look at this vibration string. Example of infinite interval here can be the guitar string, where our uxt now represent a transverse displacement at time t at the position u. So the equation is given as the second derivative in time equals to c squared the second derivative of x. Okay, and now x here is in infinite region. Okay, now you have the initial condition as when t is 0 is given by fx, and then when t is 0 there's another condition where partial u over partial t x 0 equals to gx. So this infinite domain here represents vibration of a very long string with initial displacement and initial velocity. Now I've already explained to you on my previous video. This fx here is my initial displacement and this gx here is my initial velocity. Okay, there are two approaches to solve this. Two ways to solve. So I can use, the first one is I can use Fourier transform. Okay, and then the second one approach, which is called the Alembert solution. Okay, and this is what we're going to consider in this video. So this Alembert solution here is to make change of variable that convert PDE in an easy way to solve. Okay, so let's look at solving this equation given here by using Alembert solution. Okay, so if everyone is ready, let's look at solving this PDE. I'm gonna write the Alembert approach. Okay, so what we do now will be, so the first step we want to do is, let me just write it down. The step 1 that we're going to consider is replace uxt by making the change of variable involving psi and eta. Okay, you have psi and eta. Okay, to make that changes, we introduce two terms involving psi and eta, such that my psi equation is equals to x minus ct, while my eta equation is x plus ct. Now by the chain rule, okay, I can get equation involving psi and eta. Okay, so let's look at my first derivative with respect to x. So by the chain rule, I have d psi over d x plus partial over partial eta partial eta over partial x. Okay, so all you gotta do is take the derivative. When it comes to eta here, I'm just gonna show here. So if I take the derivative here respect to x, so what do I get? It's 1, and then this one eta respect to x, I have also 1 here. Okay. And then by putting into this equation 1 now, so I have partial over partial psi. Now this is 1 plus partial over partial eta 1. So that will give me partial over partial psi plus partial over partial eta. Okay, that's the derivative with respect to x. Now for the derivative with respect to time, similar approach. So what I have here, similarly I will have partial respect to partial xi and partial xi with respect to time, plus partial with respect to eta, now partial eta with respect to partial time. So looking back into our equation respect to xi and eta here, this one here, respect to time now, taking the derivative with respect to time, I have minus c. And this one, eta over time, I have c. Okay, putting into this equation now, I have partial respect to partial xi minus c plus respect to eta c. So therefore I have this equation involving psi and eta. Okay, so what does have to do with our uxt here? Say replace uxt by making sure. So what it has to do? Okay, let's look at our wave equation given here. Our wave equation is given by the second with respect to time equals to c squared respect to x, right? So now we wanna write this in a more standard form. Okay, so not standard form, I mean more better form. Let's look at this term here. So this term here I can also write as like this. Okay, they have the same meaning here, where this is, I can write as partial over partial t u. Okay, now you get it. So this is partial with respect to partial t. Right? So I can put this equation, there are two equations involving derivative with respect to time here. So I have minus c partial over partial xi plus c partial over partial eta. Look at partial respect to time, and then there I have another one. This is for this one. Now for this term here, I have another one of these, which is negative c partial over partial xi plus c partial over partial eta, and then u. Okay, so we got to be careful when we want to expand this, okay, because this u term, so obviously you have to multiply this term here, expand, so it will end up with something like this. Okay, c squared partial u over partial xi squared minus 2c squared partial squared u over partial xi partial n. Okay, so the best way for this one, so this one, see, I have partial xi over partial n, and then I have partial xi over partial n. So there'll be 2 of that c squared, and then plus, now this term here will give me c squared partial squared over partial n squared, and don't forget my u here. Okay, so this is my UTT, in other words. Okay, now similar approach I'm going to use for my second derivative involving x here. So I can write it as partial squared u over partial x squared. Okay, now although I have c squared, I'm just going to add it later on. So this term here now, what I have, I can write a similar approach to my time just now, where the derivative of x, take the derivative of x with respect, for my u here. Okay, now what is partial over partial x? So this is the one we have computed earlier on. So I have partial over partial xi plus partial over partial eta. Okay, let's substitute that. Partial over partial xi plus partial over partial eta for this term here. Now this term here, I will have 2 of that. Okay, and then don't forget my u term. So similar approach, I have to expand and multiply. Okay, multiply the equation. So I have the second derivative. Okay, so partial squared u over partial xi squared plus 2 of partial squared u over partial xi partial eta plus partial squared u over partial eta squared. Okay, so we have these 2 equations here, equation 1 and equation 2 involving xi and eta. Now this is my the second derivative back to x. Now substituting this equation, that will give me, okay, so it's going to involve a very long equation. So I have, make sure I remember what I'm writing. Okay, so I have c squared partial squared u over partial xi squared. Okay, I have 2 here. I left it out, so just correct it. And then minus 2c squared partial squared u over partial xi partial eta. Now this one plus c squared partial squared u over partial eta squared equals to, okay, where is my c squared? And then equation 2 now. Okay, this one. So I have partial squared u over partial xi squared plus 2 partial squared u over partial xi partial eta plus partial squared u over partial eta squared. Okay, so you can see that so many terms can cancel out here. This is negative, and so the term involving this and this cancels out, this and this cancels out. So we only have this term with negative 4, right? So I have negative 4c squared partial squared u over partial xi partial eta equals to 0. So what I can say here, I can say that this will give me partial squared u over partial xi partial eta equals to 0. Or I can write it as u xi eta equals to 0. Okay, now this is the equation that we have reduced and we want to solve. Okay, before I show the solution to this, let me just upload the quiz, question 1. So for those who are taking my course, please don't forget to answer and submit the solution for quiz question number 1. Okay, now go back to the solution now. So what we have here, now earlier on step 1, I said we want to replace u xt by making the change of variable using psi and eta. So we have obtained this solution. Okay. Now, what is step number 2? So step number 2 is, so we want to solve the transform equation u psi eta equals to 0. Okay, so how do we solve this equation? Okay, this equation can be solved easily by two straightforward integration. Okay, so integration with respect to psi. Okay, so we want to integrate twice. So another way to write this, if you are not too sure, you can also integrate in this form. Okay. Okay, so now first I want to integrate with respect to eta. That will leave me a constant, okay, of psi. Okay, and then the second integration with respect to psi, that will give me how can I write this? Maybe integrating this plus function with respect to I can say this a and b are the arbitrary function of psi and beta. Okay, so I can write this. Okay, sorry, this is respect to psi just now, not eta. So I'm just gotta make changes to the way notation. So first equation, integrate respect to eta. That will give me with partial u over partial psi equals to a psi as a function in respect to psi here. And then the second term integration will give me u psi and eta equals to integrate this one. So maybe I gotta write it down clearly. Okay, now okay, maybe this notation is, if it's very difficult to understand, let me just put it in a easier way. So what I do here, this I here, move it on this side. Okay, now I can integrate this one. So when I integrate this, that will give me u psi eta equals to, now this term, how can I integrate this? But I know that will give me a function involving b of eta. Okay, so we want to replace this in terms of f and g function. So this a psi is arbitrary. Okay, and we might write this one as a function of f involving psi with a function of g involving eta. So in place of integration a psi d psi, I'm going to write it in terms of an f. So now that is step number 2. And then we have step number 3. Step number 3 is transform back to the original coordinates. Okay, remember earlier on I've said that my xi is equals to x minus ct, and my eta equals to x plus ct. So transforming back to x and y function, x and t, that will give me f x minus ct plus gx plus ct. Now, this is a general solution to the wave equation by using D'Alembert's approach. Okay, this solution represents the sum of any two moving waves in opposite direction with the velocity c. So I must say that what is cc is the velocity. Okay, this is the one we have seen earlier on my previous video. Now, continuing the solution, we have step number 4. What is step number 4? We want to apply the given condition. Okay, this can be slightly complicated, but I need to show you. Okay, so first we want to apply, so we want to find the expression of f and g. So what is f and what is g? That's the question. Okay, so we need to apply the condition and find this expression. Okay, so first we apply the first condition. Okay, the first initial condition is given as u when time is 0 is fx. So let's do that. When time is 0, f of x plus g of x equals to the small x. Okay, now we apply the second condition. Okay, from the second condition where we have the derivative x when time is 0 is gx. So we have to take the derivative of this f and t function. So what we have, taking this derivative, so this is my equation, right? Now taking this derivative respect to time, I have f prime, I have negative c. Okay, so let me just do that. So we have the equation, this is the given equation, x minus ct plus gx plus ct. Now taking the derivative respect to time, I have negative c f prime x minus ct plus c g prime x plus ct. Now when time is 0, when t is 0 is equals to gx. So partial u over partial t 0, I have negative c f prime x plus c g prime x, which is equals to my gx. Okay, now we have equation 4 and equation 5 here. Okay, now what we gotta do, this is something like using ODE. I forgot the term that I used to use. When you have equation involving f and g, which kind of looks alike, so either one of them you differentiate, you know, so and equate this equation 5, or what you do, you can integrate equation 5 and equate with equation 4. Okay, you get the idea? So what I want to do now, I want to integrate equation 5 with respect to x from any fixed point, say 0 to x. Okay, that's what I'm gonna do. Okay, so let's do that. So my equation 5 now, I have taking out the c constant, integrate from 0 to x. So change of variable happen here. Okay, I need to change the variable. So this is x, so I'm integrating with respect to 0 to x. So I'm going to write z as the change of variable. Okay, so this is what happened here. Okay, so I am integrating. Look at the way I write this equation here. Okay, so and this is equals to, don't forget to integrate the other side, 0 to x g z dz. Okay, now what happened? So I have to integrate. So integrating this this term is gonna be slightly complicated, but just follow my instruction. Now before that, I just realized that some of you might be wondering what happened to this prime here, right? Because we're integrating equation 5. This prime here, I'm writing in terms of this. See that? Take the derivative respect to or I can, so this equation above here I can write as negative c something like this. Okay, so that means the derivative of this thing. So that's why I have the derivative respect to z, negative fz plus gz, and don't forget we are integrating with respect to d. Okay, I'm gonna bring the c to my right side, so that will give me 0 to x d over dz negative fz plus gz equals to 1 over c, integrate from 0 to x gz dz. Okay, this is not that complicated because the derivative and the integration cancels out. That will give me negative fz plus gz, z from 0 to x. Now, I cannot do much for this term here. Just leave it as it is. Okay, so all I can do is play around with my left-hand side equation by substituting when x is 0 and z is x. Okay, so that will give me negative fx plus gx minus minus become plus f0 minus g0. Okay, please don't do the mistake. Okay, you have negative, right? So when I want to use the second interval, I have to do minus will become positive and then minus for this one. Okay, and then now I have 1 over c 0 to x gz dz. Now there's something I can do with this equation here. Okay, so this is not 0. Okay, this is just mean whatever function respect to x here, doesn't matter what is it, that's a term involving 0 here. Okay, so bring this to the other side, that will give me negative fx. Okay, so we have equation 6 and earlier we have equation 4 as this, fx plus gx with big G is equal to fx. This is when we obtain the first initial condition. Okay, now what we want to do, we can decide whether we want to cancel out G, we want to find G, or we want to cancel out F, or whatever. So what we do here, let's find Gx by adding these two equations. okay, which is my equation 4 and equation 6. Okay, so what happened when I add them? This term cancels out. These two will give me 2gx equals to fx plus little f plus 1 over c integrate from 0 to x gz dz minus f0 plus g0. Okay, so this is equation for my big G. Now I can divide everything by 2. Okay, divide everything by 2. That will give me big Gx equals to 1 over 2 little fx minus, should be minus or plus, plus 1 over 2c integrate from 0 to x gz dz minus f0 plus g0. Okay, now this is equation for D. Now similarly, we can find equation fx. Find fx by subtracting equation 6 with equation 4. Okay, so let's subtract them. So when you subtract 4 and 6, what do you get? Negative, negative, that will give you negative 2fx. G and G cancels out. Okay, so similar with the other one just now, but now I have negative 2fx equals to negative fx plus 1 over c integrate from 0 to x gz dz minus f0 plus g0. Okay, now divide by 2 and multiplying everything by negative. Divide by 2. So I have fx. So negative will be positive fx. And don't forget 1 over 2, positive will become negative. 1 over 2c integrate from 0 to x gz dz. Negative fo will become, so need to mention that this 1 over 2 here is also for this term here. Okay, so if I don't do that, I'm gonna do mistake on my everything. So I have 1 over 2 for fo and g. So similarly, this one will become positive 1 over 2 f0 minus 1 over 2 g0. Okay, so let me just fix this equation here. Somehow everything is moving very slow. I don't know why. This could be due to the earlier code, that earlier video that I've been working on is still editing. Okay, let's change that so that I don't make mistake. So what happened now, we can see that we have obtained the equation for f and my big G. Okay, so I can call it, this is my equation 7, and my fx here, this is my equation 8. So we have two equations, 7 and 8. One is fx and gx. Now, since we know that, since uxt equals to f of x minus ct plus big G of x plus ct, I can substitute my f with this f and my g with this g, and don't forget to substitute my x. This is my x, okay? This is my x here. So when I see x in this equation 8, I'm going to change it to x minus ct, x minus ct, okay? So that's the changes I am going to do next. So continuing, we have uxt equals, it's going to be a very long equation. So what is f? So I have half equation 8 becomes 1 over 2 f of x minus ct minus 1 over 2c, integrate from 0 to x minus ct dgz dz plus half f0 minus half g0. That's just for my f, this equation here, plus g. Now g is my equation 7, plus, okay, g, which is my equation 7, half fx of fx, which is, for my x in g now, x plus ct. X plus ct minus, plus 1 over 2c, 0 to x plus ct, gz dz minus half f0 plus half g0. Okay, so let me just, the equation is very long, but don't get confused if you use it step by step. So for my big F here, the x is x minus ct. So every time you see x in this big F, it's going to change to x minus ct. But for my big G, the x is x plus ct. So when I'm looking at my big G, the x will be x plus ct. So this will be x plus ct, and this will be x plus ct. Okay, we are almost there, everyone. So we can see that some terms can cancel out, such as this, this. Okay, now what we have here, I can combine these two interval by changing my notation. Okay, changing my notation involving the interval. Okay, so my solution now should be half f of x minus ct plus f of x plus ct, okay, plus, if I say plus 1 over 2c, that will be this one. Okay, negative here will be positive by swapping the interval. Okay, and I have g, z, dz. Okay, so this is the solution for the infinite interval without any boundary condition. It is called, the solution here is called the Alembert solution. Okay, so we can see that this is the traveling wave. We can see that if gx is 0 on the finite interval earlier on, we got the traveling solution as this, right? Earlier on I have shown you. Okay, so which means that similarly we should get in an infinite domain from minus infinity to infinity, when this g term is 0 here, okay, so we can obtain the similar solution. Okay, that's all for today. Now I have my quiz for question number 2. Okay, so I want you to get ready for question 2. There are only 2 questions. So the questions 2 will be something like this. Okay, so solve the wave equation. This is a wave equation subject to the initial conditions, such as we have oops, what happened? So, okay, there you go, that's better. So we have ux0 equals to sine x for all x, and then b partial u over partial t x0 equals to 0. Okay, so I want you to use both. Use both the Alembert, A should be a big letter A, the Alembert solution, and the separation of variable. Approach and show that they both give the same result. That's all, everyone. So this is the quiz for question number 2. Okay, so if you have any problem, just send me a message, and all the best, and please submit your the solution to your quiz at myguru.com. That's all. Bye for now, and have a good weekend. Thank you.